So welcome to topic 2 in the Life Physics class, which is heat and diffusion. The next 6 lectures are devoted to this unit. In this topic, we'll use some of the concepts we've covered in mechanics, these include energy and force, and introduce some new concepts such as heat, thermal equilibrium, kinetic energy, and diffusion. Some of this stuff you may have seen before, either at school or in chemistry, but some topics such as diffusion are likely to be new. So let's get started. So far in mechanics, we've studied mainly a single body. We can draw a free body diagram to describe how forces are acting on this body and how it may move. But what to do if we have many bodies? So thermodynamics, in the broadest sense, is the branch of physics concerned with the study of macroscopic systems with extremely large number of particles. The study of thermodynamics is the study of systems that are too large to be understood by mechanics alone. And for many years, thermodynamics was understood only vaguely, and many results were determined only experimentally. Some of the questions this field of physics asks is, what is temperature and how is temperature measured? How does a body heat up or cool down? So let's begin by talking about temperature. This is easy as we already have a working definition of temperature that is actually pretty solid for physics. But in physics we like quantifying things, that is putting numbers on properties such as temperature, so we have to go a little bit deeper. We're going to start with the intuitive definition of temperature that everybody has. This is pretty straightforward, as this is a case where the everyday notion matches the physical definition. An example where this is not the case is acceleration. Remember, in everyday speak, acceleration is always positive. But in physics, we can refer to acceleration being negative or positive. Back to temperature. As physicists, we aim to be precise and put numbers on things. So even though you intuitively understand you have a notion of hot and cold, it requires some thought in order to have a notion of cold, for instance, that is universal. This leads us to 2 points. 1, the idea of thermal equilibrium, and 2, needing a model of the structure of matter. A basic model of the structure of matter will be important as we consider the exact definitions of temperature and later heat and internal energy and how they're all interrelated. Gases. So molecules have 3 degrees of freedom. They can translate, i.e. physically move position, say 1 centimetre to the right. They can rotate or spin, and they can vibrate. Solids, on the other hand, are more constrained. They are only free to vibrate around a fixed position, and this depends strongly on the bonding with their neighbours. So this is the model of matter that we're thinking about when we consider thermodynamics. It is a qualitative description of the hotness of a body. You might easily imagine that in a hot material, the molecules are vibrating faster than in a colder material. So now to the concept of thermal equilibrium. If you take an object that is not heating up or cooling down, i.e. it is maintaining a constant temperature, it is said to be in thermal equilibrium. Now, we have still not defined exactly what temperature is precisely, but we can talk about whether it is changed or not changed. But changing with respect to what? To define equilibrium, you need an object and an environment, or 2 bodies. If we wait sufficiently long, it is said that the objects are in a state of equilibrium. Equilibrium is where the macroscopic properties of the system, and here we're mainly referring to temperature, but this equally applies to the macroscopic properties of volume and pressure, have stopped changing. This gets us to one of the laws of thermodynamics, the so-called zeroth law. Zeroth law because it was defined first as a concept after the first law of thermodynamics was established, but it was recognised as logically coming first, so it was called the zeroth law. The zeroth law says, if A and B are at the same temperature, and B and C are at the same temperature, then A and C are at the same temperature as well. Let me say that again. If A and B are at the same temperature, and B and C are at the same temperature, then A and C are at the same temperature. This means that we can say something about the temperature of 2 bodies that are not physically connected. This is quite a profound statement and means that it is physically meaningful to measure temperature.